So far, we've been studying limits. So limits are fundamental mathematical ideas. They're also useful because they form the foundation for other fundamental topics in math. Today, we are going to look at one of these fundamental topics. I've drawn in the past a picture of these three functions to talk about the idea of limits. The point of drawing them before was that they had different values at the point we were interested in, but they all had the same limit. Today, I'm not going to ask about the limit, but I'm going to ask this other question. So this is a question I typically ask my students in class, and I say, which is the best? Now, I don't define what I mean by best, and it's vague. It could be anything. Usually, everybody always answers that one. And I say, well, why is it the best? They say things along the lines of, it does what I expect it to do. Or sometimes they say things like, there are no surprises in the graph. So everybody's intuition seems pretty strong here, and mathematicians have those same feelings too. They say, yeah, I think that first one's the best. And so math people have tried to turn that intuitive feeling into a definition that we can all agree on and work with. So after a lot of trial and error, math people have come to the realization that this is the way we should define best, or no surprises. So we define something called continuity at a point. And we'll say that a function f is continuous at a point x equals a if the limit of the function at that point matches the value of the function at that point. In this definition are built in three things. Number one, your function has to have a dot at the point you're interested in. Number two, your function has to have a limit at the point you're interested in. And number three is the important one. F of a and the limit, as you get closer to a, have to match. This is the part that avoids the surprises. So in this first case, as I get closer and closer to location a, the function gets closer and closer to a height of L. If a function is continuous, there's going to be a dot exactly where the limit took you to. Now, I've said to you before that a limit of a function is kind of like walking along a bridge. If I were to walk blindfolded along this function like a bridge and get closer and closer to there, I would think that the bridge is taking me closer to a height of L. I know in a limit that you can't actually get to your point. Continuity goes one step further. It says, now let's hop off the limit and hop onto that point. And this is the part where you avoid the surprises. In this second case, there is a limit. If you walk blindfolded along this function closer to that location A, you think you're getting closer to a height of L. So if you sent your friend walking along the bridge here blindfolded and said, trust me, and as soon as they hopped off the limit and tried to step on that last plank, they would plummet. And instead of falling to their doom, they would just land at a different height. There's a plank floating in the air there. That's definitely a surprise. We would say that this is an example of a function that is discontinuous at that point. It fails to be continuous because the limit and the value don't match. At the same time, this third picture is also a picture of a discontinuous function. There is no dot. The limit exists, so as you walk closer and closer to location A, you think the bridge is taking you closer to a height of L, but this time as you hop off the limit and step in that location, you would just plummet to your doom. There's nothing there. So the value fails to exist, so the function fails to be continuous. Our eyes are really good at seeing whether a function is continuous or not. There's an easy visual test. So the graph of a continuous function has no holes or gaps or jumps or breaks. Your eyes can see when there's a floating dot. Your eyes can see when there's a hole in the graph. Your eyes can see when the graph is broken, so the limits don't match on either side. And another way to put it is that if you wanted to draw the graph of a continuous function, you don't lift your pen off the paper. If you have a hole or a gap or a jump or a break, spots where the limit may not exist or the value of the function may not exist, in order to draw them, you have to lift your pen off the paper to hop across. None of those things could be graphs of continuous functions. Having a visual or an intuitive sense of continuous functions like this is great, but what we want to be able to do is to show that something is continuous because it satisfies the definition. We want to have a way to figure out if something's continuous without the graph. And to do that, we have to show that the definition is true. So we could say something like this. Let's prove that the function x squared minus 6 is continuous at x equals 0. So number one, we need to show that the function has a value. It does. Number two, I need to show that the limit of this function exists as I approach 0. This is a very simple function. There are no possibilities for 0 in the bottom, so I can use the limit laws right away. I don't need to worry about one-sided limits in this particular case, and I will end up with a limit. So the limit exists. And moreover, the value of the function equals the value of the limit. And all three of these things together tell me that the function is continuous at x equals 0. And so this is how we prove that a function is continuous at a point. Now, to verify it, the graph of this function, x squared minus 6, is a parabola that's been shifted down 6 units. So as I get closer to the vertex here at 0, it has a dot, it has a limit, and both of them match. In the next video, we're going to talk about how to extend this definition to more than one point, because all we've talked about now is continuity at a single point.